We were talking about stoichiometry at our last meeting, and we used this basic pizza and learned how to predict, how many pizzas we could make from how much sauce or how much cheese, right? And then we applied that to chemical equations. So we're going to go a little bit further with that. And let's answer this question. If we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce, how many pizzas can we make? Three. Yeah, so how do you figure that out? No, it's 3 actually. So we can think about a question like that and come up with an answer and not necessarily know how we did it, right? Because it just kind of makes sense to us. What we're doing, consciously or not, is we're looking at each ingredient, and 4 crusts, I could make how many pizzas? 4. 10 cups of cheese, I could make how many pizzas? 5, because I need 2 cups of cheese, right? And 15 ounces of tomato sauce, I need 5 ounces for each pizza. So I'm going to run out of tomato sauce when I've made 3 pizzas, right? So 3 pizzas is the most I can make, because then I've run out of sauce and all I've got left is crust and cheese, and that's not pizza. Maybe it's cheesy bread, but it's not pizza, right? So that's it. I run out of something, the making of pizza ends, okay? So let's just look at how we would write that out, maybe to show someone else what we were doing. So 4 crusts and 10 cups of cheese and 15 ounces of sauce. And these are just going to be 1 conversion factor conversions. We're going to go from crusts to pizzas, from cheese to pizzas, and sauce to pizzas. So the recipe tells us that there's 1 crust needed for every 1 pizza. So I get 1 pizza from 1 crust, and I could make 4 pizzas. And it probably seems silly to write that all out, but that's what we're doing. And then this is the one we did earlier. We get 1 pizza for how much cheese? 2 cups. And we know that because the recipe tells us, right? So those units cancel out. This gives me 5 pizzas. And then the last one, pizza, and then 5 ounces of tomato sauce. So 1 pizza, 5 ounces of sauce. So 15 divided by 5 is 3 pizzas. To figure out how many we can make, we're taking each ingredient and figuring out how much we could make, and then our answer is the smallest number, right? We can make 1 pizza, we make 2 pizzas, we make 3 pizzas. We go to make the 4th one, there's no sauce, right? And the 5th one, there wouldn't be any crust either. You just put some cheese on a pan and stick it in the oven. It's not pizza, right? This is the same thing we're going to do with chemical reactants, okay? So here, this ingredient would be called the limiting ingredient, right? This is the one, the sauce, limits how many pizzas we could make. If we had more, we've got more crusts and cheese, we could make another pizza. But this one limits. Same thing is going to happen with the chemicals. One of our reactants will run out. And when that runs out, the reaction stops. That's the limiting reactant. And that tells us how much product can be made. So here it is in pictures. We've got enough crust for 4 pizzas, right? Enough cheese for 5 pizzas, but only enough tomato sauce for 3 pizzas. So this is the least amount of product, and so this is the limiting reactant. Any questions? So we call the tomato sauce the limiting reactant or limiting reagent. We identify that because it's the one that makes the least amount of product. The maximum number of pizzas that we can make is called the theoretical yield. And that's the amount of product in a chemical reaction that can be made from the limiting reactant. And that is assuming that everything goes perfectly, which of course, does anything ever go perfectly? Not really, no. But the ingredient, crud. So the ingredient that makes the least amount of product of pizza is limiting reactant, and that determines how much you can make, which is the theoretical yield. So in a chemical reaction, just like when you're cooking, it's likely that one of the reactants will get used up before the others. Because if you set out to make pizzas, are you going to end up with just the right number of crusts, cheese, all your ingredients? If you go to bake a cake, do you just have just enough of all the ingredients to bake a cake? No, because you had to buy a dozen eggs even though you only need 2, right? And so you never come out completely even when you're cooking. And that doesn't happen in chemistry either. So one of the reactants gets used up, and when that happens, the reaction stops. No more product can be made. So the reactant that limits the amount of product is called the limiting reactant. Any other reactants that are left over, that aren't completely used up, are said to be in excess. There's extra of them. So those are the excess reactants. How much product actually gets made is cryptically called the actual yield. Right? There's the theoretical yield. In theory, we could make this much. And then there's the actual yield. And so if you think about making pizzas, things could happen, right? You've got enough stuff to make 3 pizzas, but what if you burn one? Because you were watching a YouTube video about kittens, right? And you lost track of the time and you didn't hear the timer and you burned it. Well, that one's not a pizza anymore. It's like charcoal. Or you drop one on the floor, or the dog steals it, or, stuff happens, right? So you could have made 3 pizzas, but life happened and you only got 2. So 2 is your actual yield. That's how many you actually get. 3 was the theoretical yield. If nothing went wrong, we could have had 3 pizzas. And so what we used to see how efficient we were at making pizzas is something called percent yield. And so this is the actual yield divided by the theoretical yield times 100. So if everything went perfectly, your percent yield would be 100%. If you didn't make anything, you screwed everything up, then it would be 0%. And almost always it's going to be somewhere in between. So this is the equation for percent yield. And this follows the pattern of percentage where it's the part that we're interested in, the part that actually got made, divided by the whole, the maximum that could be made, times 100. So the part over the whole times 100. And this is just defining the other terms. Limiting reactant is the reactant that gets completely used up. It limits the amount of product. The reactant in excess is what we have extra of. Theoretical yield, how much could possibly be made. Actual yield, how much actually gets made. And there's that equation again. So that's kind of a useful summary slide. So let's apply these concepts to a chemical reaction. So we looked at balancing equations using this combustion of methane reaction. So 1 molecule of methane and 2 molecules of water make 1 molecule of CO2 and 2 molecules of, I said water somewhere. Yeah. CO2 and water. Okay, so the equation here implies that 1 molecule of CH4 reacts with 2 molecules of O2, right? So if we have 5 molecules of methane and 8 molecules of O2, which one's the limiting reactant? Which one gets used up first? Well, we can do the same thing we did with the pizzas. So we have 5 methane molecules, and we can see, well, how much product could be made? Now, this one has 2 products. You can just pick one of them, but you need to use the same one for everything. So let's just look at CO2 since it's the first one. Let's calculate how much CO2 can be made from the amount of methane that I have. Well, 5 methane molecules, 1 methane for every 1 CO2, I could make 5 CO2 molecules. And also says I have 8 molecules of oxygen. So 8 molecules of oxygen, I get 1 CO2 for every 2 molecules of oxygen. So that would be 4. Let's just go back here. So there's 2 of these for every 1 of those. So the methane would make 5, but the oxygen would only make 4. The reaction stops when you run out of an ingredient, a reactant. And so this is the most that can be made. So the oxygen is the limiting reactant, and the amount of product it can make is the theoretical yield. Any questions? These conceptual connections, in theory, have no math in them. They're conceptual, right? Nitrogen and hydrogen gas react to form ammonia according to this reaction. So we have 1 molecule of nitrogen and 3 molecules of hydrogen. So here we have a flask containing a mixture of reactants, and then we're asked which of these other flasks, A, B, or C, best represents the mixture in the flask after the reactants have reacted as completely as possible. What's the limiting reactant? Which reactant is in excess? Well, we need 3 hydrogen molecules for every 1 nitrogen molecule. So we can just kind of group these here. So those guys there would make 2. Those would make 2 ammonia molecules, right? And here's another nitrogen, and it can react with 3. So that's going to make another 2. And what do we have left over here? We have 2 hydrogen molecules. So over here, could this be the correct answer? No. We can make 4 ammonia molecules because this one will make 2 and this one will make 2. But we still have the hydrogen that's left. It's just sitting there. It doesn't disappear just because it wasn't wanted or couldn't be used. So this isn't right. Does this one work? No, because what's happened here is that only one of these groups has reacted and the rest has not reacted. There's still possibility for more reactions. That's not going to work. So this is the correct one. We've got 4 of the ammonia molecules that we've made, and there's the 2 leftover hydrogens. You see how that works? It's nice to have the pictures because, if you can picture it in your mind, then when you're doing the math and stuff, it makes a lot more sense. So we don't measure things in moles, do we? We measure things in masses. So we have to add some steps on here. So we've got a mass of an ingredient. We have to convert to moles. And then we can figure out the moles of the product that can be made. Right? And this is the way the book shows it. And this is a valid method. But I find it can be a little confusing. So it's not how I'm going to do it. I think a more straightforward way is you take each ingredient, each reactant, and you go grams to moles to moles to grams, and you find the mass of the product. And then you look and see which one's smaller. That's your answer. This other way saves you one calculation, but you have to do more thinking, and so I don't know that that's necessarily a good idea. Let's just make that completely disappear. So we have one ingredient, magnesium. We'll go from grams to moles of product to mass of product. The other ingredient, oxygen, grams to moles to mass of product. And then we're just going to choose the smaller. Choose the smaller answer. Okay. If we want to know which is the limiting reactant, let's say this one was smaller. The limiting reactant is the one that gives us the smaller number. So let's do an example. Reaction mixture contains 42.5 grams of magnesium and 33.8 grams of oxygen. What is the limiting reactant and theoretical yield? Suppose that the actual yield is 55.9 grams. What is the percent yield? Let's just calculate all the things. Well, always a good idea to start by just identifying the numbers, the things that were given in the problem, right? So we've got grams of magnesium and grams of oxygen, and then we've got the actual yield is this. And then they're asking us several questions, aren't they? They want to know what the limiting reactant is. They want to know the theoretical yield, and they want to know the percent yield. So we have our balanced chemical equation, and this is the key to the whole thing. So let's use that to organize this information. So we have 42.5 grams of magnesium. I'm going to write that down here, 42.5 grams of magnesium and 33.8 grams of oxygen. So the limiting reactant, that answer is going to be either magnesium or oxygen. The theoretical yield, what's that going to be? It's going to be how much of this could be made, right? So one of the things we're trying to find is how many grams of this can we make? And it's like with the pizzas, we have to deal with the amounts of ingredients that we have, and when one of them runs out, we stop. So we're going to go grams to moles to moles to grams for both of them and identify the smaller one. Okay, that'll give us this. Then we look at which reactant gave us the smaller number. That'll tell us the theoretical yield. The percent yield, we're going to have to do a calculation with an equation. Percent yield is actual over theoretical. I like to call him Theo times 100. Any questions? So I'm going to set up two equations. So first I'm going to do, let's see, how could I do that? First I'm going to look at this one. I'll write that one in orange, maybe that'll help. So the idea here for everything is grams to moles to grams. So 42.5 grams of magnesium. And most stoichiometry problems are going to have 3 conversion factors. Grams of magnesium to moles of magnesium to moles of product. Here there's only one product, MgO, to grams of product, MgO. Now that's an MN. There we go. Grams of magnesium down here. Moles of magnesium down here. Moles of magnesium oxide down there. So here we've got our moles in the middle. Where do we get the numbers? The big numbers in the equation, right? The coefficients. So we have moles of magnesium down here, and there's a 2 in front of that one. So 2 moles of magnesium is going to make 2 moles of magnesium oxide. That's the simple part. Now this problem is not as messy as the ones we did on today's Wednesday, the ones we did on Monday, because we've got much simpler things here. So here we have an element, just magnesium, so we don't have to calculate the molar mass, we can just look it up, right? So the periodic table tells us that 1 mole of magnesium weighs 24.31 grams. And then we will have to do a little bit of a calculation here for the magnesium oxide. 24.31 grams plus 16 for the oxygen. I don't want to try that in my head. 40.31. So over here, 1 mole weighs that many grams. So then we can calculate if all the magnesium gets used up, how much product will we make? 42.5 divided by 24. I did. Thank you. Thank you. Yep. I'd like to say I did that to just see if you're paying attention, but that's not the truth. Okay. Times 2 divided by 2 times 40.31. And I'm starting with 3 sig figs, so this would be 3 sig figs. There's 3 sig figs. I want to write down 2 extras. So grams of magnesium oxide. That's assuming we have enough oxygen, right? So because they gave us the mass of the other reactant, then we also have to look at that one. So we'll do a second calculation. Oops. That's purple. Can you tell that's purple? Okay. Purple and orange. I don't know. I'm getting ready for Halloween. Again, we're going grams to moles to moles to grams. But we're going to start with the other reactant. We're going to the same product, though. So 33.8 grams of oxygen. Grams to moles to moles to grams. And then we stick the units in the denominator. This unit, grams of oxygen, comes down here, so those are going to cancel out. Moles of O2 comes down here, so it cancels out. The same thing we've been doing the whole semester now. We've got moles in the middle. We're looking at a balanced chemical equation. It only takes one oxygen molecule to make 2 MgOs. So 2 moles of MgO for every 1 mole of oxygen. Oxygen, its formula here is O2 because it's a diatomic element, and so the molar mass for that is 2 times 16, which is 32 grams. So 1 mole of oxygen weighs 32 grams. And look at this guy at the end. That last term is exactly the same, right? That's part of why I think instead of stopping here and finding moles and messing around there, let's just go all the way to the end because you already know what this number is anyway. And then there's just less thinking. So 40.31. We already figured that one out. So 33.8 divided by 32 times 2 divided by 1 times 40.31 equals 85.154 grams. How much product can we make? 70 grams or 85 grams? 70 grams. Because when we get to this much, we run out of magnesium. We can't make any more. Occasionally people get a little creative and they say, well, this will make that much and this will make that much, so I'll add these two together. Well, if you think about that with pizzas, that's ridiculous, right? And yet with chemicals, it doesn't seem so ridiculous, and yet it is. So I am choosing just the smallest number. So the smallest number is this one. That is my theoretical yield. So I would want to round that, right? So that would be 70.5 grams MgO is the theoretical yield. So that's one of the questions. What's the theoretical yield? What's the limiting reactant? It's the magnesium, right? Because this is the one that we used up. There was more oxygen. We could have gone farther, but we didn't because we ran out of magnesium. So this is our limiting reactant. That's an L. Kind of looks like a 2. L. Limiting reactant. Okay? Then they're asking for the percent yield. Percent yield uses an equation, actual yield over theoretical yield. We calculated the theoretical yield. We're going to use the unrounded version. They gave us the actual yield. In a problem, they have to tell you what the actual yield is. If you're doing an experiment, the actual yield is like the actual amount of copper you ended up with, right? It's how much you actually got, and you would be measuring that yourself. But if you're not doing an experiment, they have to tell you what it is. So maybe we do this one in blue. Oops. So the percent yield is equal to the actual yield, which they told us right here, 55.9 grams, divided by the theoretical yield. We want to use the unrounded one, 70.472 grams, times 100. The grams cancel out. 55.9 divided by 70.472 times 100. So this should also have 3 significant figures, 79.3, 22, 79.3%. That's our percent yield. Any questions? Can't remember, it was probably on worksheet 4. There's at least one question like this, where it's asking you for multiple answers, right? And so if you don't identify which of these answers is correct, you did a lot of work, but you didn't tell me an answer. If you don't identify which is the limiting reactant, then it's not correct because you haven't actually chosen anything, right? So you need to choose it. And, I don't require a complete sentence or anything, just, LR and point to this one, that's good enough. So magnesium's limiting reactant, 70.5 is the theoretical yield, 79.3% actual percent yield. Let's do another one. Ammonia can be synthesized by the reaction 3H2 plus N2 makes 2NH3. We looked at this with the little pictures. What's the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? Well, they're giving us a mass of hydrogen and a mass of nitrogen. Those are the things with the numbers. And here's our question word, what? We want theoretical yield of ammonia in kilograms. So I'm going to take these numbers and write them under the chemical equation. So hydrogen, 5.22 kilograms. Nitrogen, 31.5 kilograms. They want the theoretical yield of ammonia in kilograms. It does say limiting reactant up here. Nothing in the problem says anything about a limiting reactant, though. You can recognize when you have a limiting reactant problem because you're going to get masses of 2 or more of the reactants. If they just told us about one, it'd just be grams to moles to moles to grams and we're done. But they gave us masses of both. And so we do the grams to moles to grams twice and pick the smaller answer. Of course, this isn't grams, is it? It's kilograms. So we're going to go 5.22 kilograms. What does kilo stand for? Times 10 to the 3. Way back in worksheet 1, we had some problems where we took numbers like this and wrote them in scientific notation without the prefix. Right? We substituted in what the prefix meant. So instead of kilograms, kilo stands for times 10 to the 3 grams. That's one thing you can do to shave off that first conversion factor of kilograms to grams. So we can do that with the other one also. 31.5 kilograms instead of kilo, I'm going to write times 10 to the 3 grams. So the first one is hydrogen, and the second one is nitrogen. So grams of hydrogen to moles of hydrogen. 2 moles of the product. Again, there's only one product, so we don't have to choose. And then grams of NH3, but they want it in kilograms, right? Kilograms of NH3. It's getting smaller and smaller. Grams of H2, moles of H2, moles of NH3, grams of NH3. Here we have our moles in the middle. This comes from the balanced chemical equation. Moles of NH3, we're making 2 moles of NH3, and that needs 3 moles of hydrogen. We need the molar mass of hydrogen, which is 2 times the mass of hydrogen. One mole weighs 2.016 grams. We need the molar mass of ammonia. So 1 mole is 17.034 grams. And then here we need to put, we have kilo in the numerator, we need to put what it means in the denominator. 1 kilogram is 1 times 10 to the 3rd grams. .403 kilograms. We're going to do something extremely similar down here, right? Grams to moles to moles to grams, and the very end is going to be exactly the same. So here we're starting with grams of nitrogen. We're going to go to moles of nitrogen. Then we're going to go to moles of ammonia, to grams of ammonia, and finally to kilograms of ammonia. Grams of nitrogen, moles of nitrogen, moles of NH3, and grams of NH3. This is grams of ammonia to moles of ammonia. This is the same thing. We don't need to do any calculating. It's the same number. This is kilograms and grams. Again, it's the same number. Didn't leave much space, but there it is. The mole ratio, look at the equation. There's an implied 1 before the nitrogen, and there's a 2 before the ammonia. And then the molar mass of N2 will be 2 times 14.01, or 28.02 grams. So this one gives me 38.299 kilograms. What is the theoretical yield? This is the smaller number. It's this one. So my theoretical yield equals 29.4 kilograms of ammonia. Any questions? You should have done problems like this in Chem 3A. Maybe you don't remember how to do it. Hopefully you remember, oh yeah, I remember seeing something like that, right? There's a lot of things in chemistry that the first time you learn them, it just doesn't make any sense. And then the second time you learn it, you're like, oh, well, that's how that worked. Okay. So hopefully some of these things are working like that for you. 29.4 kilograms. Here's another one that's giving us masses of two products. It's saying that this reaction produces 72.3 grams, and it's asking for the limiting reactant, the theoretical yield, and the percent yield. I'm not going to actually do this problem because it's very similar, and we have other things we need to do as well. This 72.3 grams of iron, what are they telling us here? This is the actual yield. They didn't come out and say the actual yield is this, but this is, it produces this, that's your actual yield. The theoretical yield, you're always going to calculate by doing the two equations. Then the percent yield, you're going to take your actual yield divided by the percent yield.